Okay, so what I want to say is that there is essentially no difference in the truncation error analysis for different type of equations. If this is a two-dimensional heat equation, you have d dt equal to the second order derivative in x plus second order derivative in y. You do exactly the same truncation error analysis. What's different between the elliptic equation and the other types of equation is the stability analysis, right? That's the analysis of how does this approximation error translate into the solution error. In previous equations, we looked at heat equation and advection equation. In both of these equations, there is a time derivative. And the error equation becomes an ordinary differential equation with a source term. And the source term of this ordinary differential equation was this truncation error, right? And the dynamics of this ordinary differential equation determines if the truncation error is going to be amplified or it's not going to be amplified. That is stability. So if I have a stable discretization and my truncation error is small, then I know my solution error is small, right? So basically, previously what I had is stability plus small truncation error leads to small solution error. We'll see how this is going to be reflected in this particular case. In this particular case, the analysis of small truncation error is the same, but the analysis of stability is going to be very different. So the question is, how does the tau translate into a solution error if we are solving this equation? The derivative of the second order derivative of w plus the second order derivative of y plus a known function f of xy equal to 0. How do we analyze stability for that? All right, the analysis of stability, actually the process is different, but the principle is actually the same. The principle has always been that if you are able to substitute, if you are able to substitute the analytical solution into the numerical approximation, how would the error look like? So remember, now let's use a superscript to distinguish between the analytical solution and the numerical solution. Okay, so this is the analytical solution. And the numerical solution is different. The numerical solution satisfies a different equation. So wij plus wi minus 1j minus 2wij, right? So this is again our finite difference formula. So my numerical solution satisfies this. If I directly subtract these two equations, I would have a difference between an analytical second order derivative and a numerical second order derivative. But that is not the truncation error, right? Because the truncation error requires the numerical and analytical second order derivative to be operated on the same function. And here I have different functions. The analytical differential equation is satisfied by the analytical solution, while the numerical differential equation is satisfied by the numerical equation, numerical solution. So W and WA are different in this case. So how do we make them the same so that their difference actually gets us the truncation error? Well, the thing to figure out is, the thing to do is to actually substitute the analytical solution into the numerical solution and then subtract. Okay, so the process is, what if I put in this analytical solution into the numerical scheme? So all of these are analytical, and this is also analytical, blah blah blah, plus f of ij. Now this is equal to what? Is it equal to 0 still? It's not going to be equal to 0. It's equal to actually what? It's equal to truncation error, but why? How do we derive that this is actually equal to the truncation error? What we do is we actually add and subtract this guy onto this equation. So if we subtract, okay, basically if we subtract the left-hand side of this equation by the analytical Laplacian, what we get is the truncation error. And then we add the same number, right? So we have to add and subtract the same thing. And if we add the same number, what we get is actually this is equal to 0, right? So basically the second part is removed. So basically we get tau at ij, the truncation error, plus the analytical derivative. So let me just denote this with Laplacian of omega a plus Laplacian of omega a plus f, right? Because this is 0 by the analytical differential equation. This is just equal to tau ij. All right. Is it clear what we did? Okay, so good so far. So what that means is that now we can actually subtract these two equations. We have one equation satisfied by the numerical differential equation, another equation satisfied by the analytical equation. And the difference between them is actually, so first of all, we are going to cancel this f, right? It doesn't matter what f is anymore. Now what matters is the numerical Laplacian operator operated on the difference between numerical and analytical solution, which is the solution error, right? The Laplacian operator, the numerical Laplacian operator operated on the solution error is equal to the truncation error, right? So if I write down the result of the subtraction is if I define E being the numerical solution minus the analytical solution, then the subtraction gives EI plus 1j plus EI minus 1j minus 2EIJ divided by delta x squared. That's the result of subtracting the first term, right, between these two equations. Okay. Plus E of ij plus 1 plus E of ij minus 1 minus 2EIJ. That's the result of subtracting the second term in these equations, right? So it's all because the numerical operator are linear operators. Now the third term, the Fij, they cancel out. The only thing left is delta ij, which let's move to the left hand side. We get a plus delta ij, right? So this minus this, we get minus delta ij. Moving to the left hand side, it's plus delta ij is equal to 0. Okay, so we see that we have almost exactly the same equation as the original numerical scheme, right? So just to look at how similar the error equation is with the numerical solution. I'm just replacing the numerical solution W with the solution error E, and then I'm replacing the known function right hand side Fij with the truncation error, right? Same equation. Just the solution is replaced by the error. The f is replaced by tau. Okay, so again, we derive the conclusion that the stability of the differential equation, which in this case is how the right-hand side is going to affect how the magnitude of the right-hand side is going to affect the magnitude of the solution. That is stability. Or in some sense, the I can define stability as the magnitude of E as a vector divided by the magnitude of tau as a vector. So this defines stability, right? And in general, because I actually don't know what tau is, I'm usually looking at the maximum possible, or like in mathematical term, the supremum. Because I mean the collection of possible taus is actually infinite. So mathematically, the maximum over infinite set is called the supremum over all possible taus. And tau here is a vector. It's a vector consisting of the value tau ij across all the possible indices I and j. Right? I goes from 1 to n or 0 to n depending on initial condition, and the j goes from 0 to m or 1 to n minus 1 or whatever. Okay, so this is the definition of stability.